All right, welcome to this video. Today we are going to do rolling force a rolling force example. So we're going to analyze the rolling force and power of an annealed copper strip that is 9 inches in width. So it's the material is 9 inches in width. And it's a annealed copper. Okay, the starting thickness, so HO is going to equal 1 inch, and the final thickness in one pass is going to be 0.8 inches. Okay. The rolling radius, so the radius of the rollers is going to be 12 inches. And it's going to rotate at 100 RPM. All right, so let's just draw that here. So we have a roller there and another roller here. It's a flat roller. So the material is 1 inch here. And it's going to be squished down to 0.8 inches in one go. And then these are going to be rotating, these rollers, at 100 RPM. And they have a radius of 12 inches. Okay, so to determine the force, we need to, basically we need to know the formula we're working with. So force is pressure times area. So we have a contact length here times a width. So that's going in this direction. We have a width of 9 inches. And then that's going to get multiplied by our average true stress. So let's just write that formula out. So F is equal to our contact length times our width times our average true stress. Okay, so we now need to figure out L. So L from our previous videos was square root of R times the difference between the beginning thickness and the final thickness. So we have all this information. We know our rolling radius, we know our beginning thickness, and we know our final thickness. So let's go ahead and calculate it. So this is going to be equal to the square root of 12 times 1 minus 0.8. And so L is going to be equal to just going to pull up the calculator here. So 1 minus 0.8 is equal to 0.2 times 12, so 2.4, and we want to take the square root of that. Okay. A bit unfamiliar with this one, so I think it's just this one. Okay, so 1.5, let's just write that down, 1.549. Inches. And you can see the units work out as well. So you have inches times inches, which is inches squared, and then you square root it, and it becomes just inches again. So that works out nicely. So now we know our contact length. We just need to figure out our true stress, our true average stress. So to find that calculation, we have to use, we have to determine our true strain. So from this calculation, in our previous video, it was epsilon equals, or our true strain is equal to ln h, the height or the thickness of our original shape over the height of the final shape. So again, we have all of this information. So this is equal to ln 1 over 0.8. So that is now equal to, let's just pull up the calculator again. 1 divided by 0.8 is 1.25, and we'll take the natural logarithm of that, and it's 0.223. Okay. So we'll grab this figure here. This is from the textbook. And let's just figure out where that is. So our formula for average true strain is y average is equal to our true stress at the annealed state plus the true stress at the true strained state. So I'll just call that T epsilon over 2. So annealed copper is this blue line right here. And so let's just move down a bit for a little bit of room. You can see here that this is where it intersects between 0 and 20. It's about 10,000, 11,000, or 12,000. It's kind of hard to see, but I'm going to go with, looks like it's closer to the 20, so 12,000. So 12,000 plus that 0.223. So we'll just mark this one too. So 0.4, so 3 would be here, and then 0.25 would be here, so 0.225 would be here. So that's pretty close to where we're at. And if we draw a line upwards and then a line across, we get about 40,000 psi. And then we'll have to divide that by 2. And so we'll get a y-average of, pull up the calculator again, so 12,000 plus 40,000 divided by 2. So we get about 26,000 psi. Okay, so I think we have enough information to figure out our force. So we have our contact length, we have our width, and we have our average true stress. So force is equal to our contact length, which is 1.549, 1.549, and so we'll multiply that by our 9 inches in depth, or width, sorry, and then we'll multiply that by the 26,000. Okay, and we'll figure out what we got. So 26,000 times 9 times 1.549 is equal to 362,466. Pounds. So that's quite a few pounds of rolling force. It's pretty huge, actually. Okay, so if this is rotating at 100 RPM, what's the power requirement to drive these rollers? So let's figure that out. So power, we'll use this formula here. So power is equal to 2 pi force times contact length times our RPM over 33,000. Okay, so again, we have all of our information. So we'll do 2 pi times 362,466 times 1.549 times 100, all divided by 33,000. Okay, so multiply 362,000 by 2 pi, so 2 times pi, and then we'll multiply that by the 1.549. I don't think I have my pi in there. There we go, it's in there now. And we need to multiply that by 100. And now divide the whole thing by 33,000. Okay, and we get about 10,690 horsepower. But I believe I've made a mistake here, because our contact for this thing, I just remembered that our contact length needs to be in feet. So don't get hung up on that one. It just seemed a little bit high for the horsepower to be 10,000 horsepower. So this is actually supposed to be divided by 12. So that means that this number here needs to be divided by 12. And so I get about 891 horsepower. Okay. So that is it for this example of rolling a flat piece of copper, annealed copper, from 1 inch to 0.8 inches with a 12-inch roller. All right, I hope you enjoyed. Let me know if you have any comments in the comment section below, and we'll see you in the next video.